All right. These videos tend to not do as well because there's no corresponding lead code posts that I can share it to. But here goes. Introduction to cyclic sort. It's the next pattern we're going to be evaluating within the next, I think, 5 videos. And so it's the pattern, it's real world applications and some problems we can solve with it. Okay. Now they go into all this stuff, but which I'm not sure is super useful. To be honest, I just like to see examples as quickly as possible. So key term, cyclic sort is a simple and efficient in-place sorting algorithm used for sorting arrays with integers in a specific range, most of the time from 1 to n. And in place, it places each element in the correct position by iteratively swapping it with the element at a position where it should be located. And it continues to all the elements in your proper place. Okay. All right. So if we're looking at this, for instance, right, this is the type of thing that lends itself to what we're dealing with. We have these numbers, and you see they go from 1 to 6, and we want to put them in the right place. So with cyclic sort, you start from it, find its correct position, and swap. And that's the bulk of it, really. There's 6, so you stay here until the right element. You stay in and at the particular index till the right element gets there. And then when that happens, you move to the next one, you check it's in the right place, then you get here, and you stay there to the right one is in the right place. And in this case, they messed up because they were supposed to in the diagram because 3 is supposed to be here and 4 is supposed to be here, but you get the point. And um, so all right, so there's a wall of text we have to go through. Let's just run through it real quick. So they're asking, is there a way to determine whether to use cyclic sort on a given unsorted array of integers? And the answer is yes. We can identify cycles within the array, which are nothing but the subsequences of numbers that are not in sorted order. A cycle occurs when there's an element that is out of place, and swapping it out with the element at the correct position moves another element out of place, forming a cycle. Okay, so the unsorted arrays with numbers ranging where n is the length of the array are guaranteed to have one or more cycles in them. Now the slides illustrate a traversal technique utilized for identifying cycles present in an array. Okay, how do I find cycles? So I start from 3, then I go to where 3 is supposed to be, which is here. And then where I see 2, then I go where 2 is supposed to be, which is here. And then I go to where 1 is supposed to be, which is here. And then I ended up having a cycle there. Then if I, as a first cycle, and then if I go to the next element out of the cycle, I go here, this is supposed to be there, and then this is supposed to be back here, so that's another cycle. I guess that's what they're trying to say. Not sure why that is useful, right? Because as you see, it doesn't come up again after the fact. But once we find a cycle, we can remove them with cycle sort. And this is how the cycles are removed. Um, so the swapping, the same swapping we just explained. So we stay here, the cursor stays here until the swapping is done. Yep. And then we deal with this one till it's done. And then the cycles are removed. So in practice, the process of identifying cycles and performing cyclic sort is seamlessly integrated and considered as one cohesive operation. The separate illustrations provided are merely for explanatory purposes, simplifying the underlying understanding of the overall process. So unlike algorithms with nested loops or recursive calls, cyclic sort achieves the linear time complexity due to its streamlined approach of iteratively placing each element in the correct position within a single pass through the array. Okay, so it's better than other algorithms with all of n time. I think most other sorting algorithms are log of n log n, and then it's fast and reliable, especially for small arrays. Moreover, it doesn't require extra space because it sorts everything in place. So it's efficient in specific scenarios, but has limitations, and that includes limited range, as contingent upon the range of elements being limited and known beforehand. And now, when dealing with arrays with an unknown or expansive range, it may not perform optimally. For instance, we have an array of prices of goods ranging from 1 to 100, it would efficiently organize them. But if the price extended beyond 100 or was unknown, then this is not going to work. And it's not a stable sort. And it may alter the relative order of equal elements during the sorting, which could be undesirable in scenarios where maintaining the original order is important. For example, in a task queue where tasks with equal priority should be processed in the order they were received, this might reorder them, the ones with the same priority, disrupting the original sequence. So it's not good for non-integer arrays either. So it's for sorting arrays of integers. And attempting to use it on non-integer arrays may not produce the desired outcome. Suppose we want to sort an array of names alphabetically, then this is not going to work. It's also not suitable when multiple attributes play a significant role. So arrays of integers, so it may not handle cases where the input has multiple attributes associated with it. For example, given an array containing objects representing employees, where each object has a name, age, salary. If you want to sort it with respect to all three attributes, then this cyclic sort on just salary may not produce the desired outcome. This is because the other two attributes play an equal role in deciding the final order, so we can't just take one attribute while sorting the array. Normally, it's quite easy to know when to terminate the algorithm for cyclic sort. If we have the input array of n from 1 to n, then it would end once every element of the array has been traversed from 0 to n minus 1. However, it gets tricky to determine the termination when the input array of length n doesn't contain every number from 1 to n. In such a scenario, we'll end up either in an infinite loop or incorrectly placing elements in their respective positions. In both cases, it is essential to incorporate appropriate error handling mechanisms or termination conditions within the algorithm to prevent infinite loops and ensure correct sorting outcomes. Now, this may involve additional checks for duplicates or missing values, as well as adjustments to the sorting logic to accommodate such scenarios. Okay. The examples represent two such scenarios where termination of it requires additional checks. Okay. So set mismatch. We have numbers from 1 to n. We want to find one number that is repeated and another that is missing. We'll come to this later, I'm sure. But I mean, if we walk through the slides real quick. So swapping them. The same swapping we did just now. So we'd have to do some extra checking. Okay. Then we terminate the sort. Okay, then you loop over it again. All right, I think it's one of the problems we'll see as we move on. The kth missing positive number. So the kth missing positive number is 3. Find the third missing positive number. So how does this one work? Okay. This one isn't super clear to me. But I think we evaluate something similar to this down the line, so we can skip it for now. Yeah. How to know if your problem matches this pattern. And this video is already 8 minutes long, but it matches it if we have a limited range. Okay, if we know it goes from 1 to n, right? If we're finding missing or duplicate elements. And then if we're dealing with non-integer values or not an array or a stability requirement, then this pattern doesn't work. Yeah, real world problems, right? That's have to do with this pattern. We have computational biology, right? Where and distinct genes. Play card sorting. We have a deck of playing cards. So you can rearrange them. We have data validation. We're dealing with data sets that are expected to have distinct values within a certain range by applying the sort. We can identify missing or duplicate values, which can help in validating the integrity and accuracy of the data. Okay. And package delivery. We can map the addresses to integers in a defined range and use cyclic sort to optimize the route Rearranging the addresses based on the mapped integers, minimizing travel time. Okay. All right. Okay. Then strategy. Closest number that's a palindrome. I'm gonna say that. Say this. We just saw something similar to that. Boom. Then you can see the explanations. Oh, not bad. That's that for this pattern. We're gonna resume with this problem in the next video. See you then.